Okay. Well, I suppose I'll just get chatting. Don't worry about it. You can keep unpacking stuff and whatever. I'm loud, so it's fine. Um, so I don't really have any announcements, really. Um, there's a quiz today. No way. Shocker. And it's going to be on graph theory. Um, I know I'm really delivering the hard hitters today. Um, and there's no class next week, so you get a break from math. But I don't think you get a big break from the rest of your stuff. You probably have homework. Eh? Well, it's something, Could be worse. Yeah, fair. Could be worse. So last class, it was kind of rapid fire definitions and topics. I introduced the idea of a graph, which is a set theoretic definition, right? You got a set of vertices, and then you got a set of edges connecting those vertices, and they're graphical in nature, right? You can sort of visualize what a graph looks like, and they're a discrete data structure, so that's a big part of why they appear everywhere in computing, because it ultimately a graph is a perfectly good way of thinking about a problem. If you look at it and you say the only thing I care about is that there are nodes and connections to those nodes. If that's what your problem set satisfies, then trees are a good data structure for it. Yeah.
What does discrete math actually mean?
Discrete usually means countable. So that means there's the notion of countable versus uncountable. Countable does not mean finite, but usually it does. You can talk about graphs that are actually infinite and they're still totally valid and fine. Uncountable is like real numbers, right? There's a mathematical concept of being countable versus uncountable. A discrete is just dealing with stuff that is almost always finite in nature. So that's why it's a good fit for computing, because computers are also finite by nature. So yeah, that's what discrete math is. So then anyway, I gave some like a history thing with the Euler trails, and I talked about a bunch of different types of graphs, like simple graphs, connected graphs, some others. Maybe I mentioned Hamiltonian graphs. I don't think so. But anyway, the point is, directed graphs. There's lots of different types of graphs that we can classify that are each individually interesting. And then once we did that, I was like, okay, let's start talking about various algorithms on graphs. So one of the ones we talked about was graph coloring. And the reason, so graph coloring on its own looks like kind of a mundane problem, in the sense of you're just coloring the vertices on a graph. It's like whatever. But you could see how it would be useful in like maps and that sort of thing. But from a computer science perspective, graph coloring is a very interesting problem, because if you ask, what is the smallest number of colors I need to color this specific graph? Or if you say, how many possible ways are there to color this specific graph? Up to permutation, right? Because this can be red and this can be green, but this could be green and this could be red, right? You swap the other, those are different colorings. And both of those problems are NP hard, which means there is no polynomial time algorithm to solve them. They're very, very time consuming to solve. They're very difficult problems. So in computing, that's always an interesting problem, because they come up all over the place in the real world. The traveling salesman problem is a perfect example of one that's sort of related to this. And when you find that news out, you're like, oh no, this problem is computationally very hard to solve. Like we're talking, I run it on a set of like 60 things and I use that algorithm. It takes hours, if not days, to complete that algorithm. Like it is not fast. It is bad. So that's why they're interesting. Graph coloring is interesting, not so much in the actual algorithm, but in the computing science behind it. Trees, though, the next thing we talked about, and that's what I'm going to spend the rest of the day talking about. It shouldn't be too long. I just want to go over some algorithms about it and some definitions. Are a data structure that appear all over the place in computing. They're actually pretty easy to implement if you know object-oriented programming, which you don't know yet, but you will learn. So when dealing with this on assignments and stuff, I will provide the data structure for you. And you just have to build the algorithms surrounding it, and I'll give you the documentation on how it all works. But then that means in the future, you will have an implementation of a tree that you can look at and be, oh, I get it now that I understand object-oriented programming. So anyway, we're just going to talk about some definitions and some algorithms. So we have this idea of a tree, and I'm just going to draw one here. I want to make sure I draw the right one. I have so many of them. So I am going to do this one. 1, 2, 3, 4. Got this tree structure. And then I've got some labelings for my vertices. The R, apparently. Apparently I forgot to add that in and just pick the letter. So anyway, this is what a tree looks like, right? We've got our root up here. And then we've got these leaf nodes and this sort of structure to it. So algorithm-wise, we often want to search this tree in an efficient manner, right? We want to either find a way to list everything in the tree, as an example, in a specific order, or we want to traverse this tree and look for something. And there are sort of two ways to do that. And they each have their uses. One of them, called breadth first search, sort of spreads wings really wide before going deep down the tree. So it would find like this stuff long before it would ever get to this one, right? So that's useful if you're trying to find the shortest path from something, right? You've got this big complicated web tree, and you're like, what's the shortest path? If you follow that algorithm, you will find the shortest path very quickly. But if you want to find the longest path, that's pretty bad, right? So the other one, depth first, goes deep into the tree first and then spreads its wings. So we'll just actually write down these algorithms and then perform them. So this is breadth first search. I think my tree is going to block my ability to write notes, but that's how it goes. So the way we do this is I'm defining it in terms of just graphs in general, because it also works for graphs. It doesn't just apply to trees. So you pick a vertex to start with. We're going to call it, let's call it B. To start with, in a tree, choose the root. Right, because it's the natural starting point of every tree. So if you want to pick a random place to start, that's a good starting spot. So what we're going to do is mark this vertex as visited. And check it. So if we're, say, doing a search for a specific node, we check this node first and say, is this the right one? Yes or no, right? If I were looking at this tree and I was like, okay, is A in it? I would go here first and I would check and I'd be like, yes, it is, right? But if it's not there, we need to decide what to do next. So if you must continue, we check all the nodes that are connected to that. So like here, we would start at A, and then we would say, all right, I'm going to check B, and I'm going to check C, right? All connected vertices. And mark them visited. And then once you've done that, you essentially just sort of keep going, right? You visit the neighbors of the neighbors that you haven't visited yet, and so on. Then visit the so-called neighbors of neighbors. Etc. Right? Just keep going in this way. So what does this actually look like on this tree? So let's go through the whole thing and sort of spit everything out. So we're going to start at the root node A, right? So we start here and we visit it. So we're going to mark it as visited. I'm just going to put a little dot to say that we visited that node, right? Okay, so we just saw A. Now we visit the neighbors of A. Usually we go left to right, just it doesn't matter, but like left to right is a natural way to do it. And then we visit those. So we're going to visit B, and then we're going to visit C. We're going to mark both of those as visited. And then we say, okay, now of these, I visit the connected ones that I haven't been to yet. So I'm not going to go back to A because I've already been there. So I'm just going to keep going. So I'm going to visit D, R, E, and F, right? In that order, because we're going to go left to right, right? We visited B and C. Now we need to visit the neighbors of B and C. So that's going to be D, R, E, and F. And then we're also going to visit G. Right, so we're going to go down all of these. And then now that we visited all those, we continue, right? There's only one more connected node, H. So we go down to that. We visit like that. You can kind of see here, right? We're sort of visiting this tree in levels, right? That's the top level, then this level, and then sort of it all sits along here, and then we go down again, right? So we're sort of traversing like this. And you can kind of see how this would work for solving the shortest path problem, right? You've got like you want to get from here to here, then you would go like this, and I'm done, right? I don't even visit these because they're not part of the shortest path, so I don't care anymore, right? So that's how it works for something like shortest path. And it's good for searching if you know that something you're looking for will be sort of higher up in the tree than deep in it. So this is one way to do it, and you can kind of see that it's very iterative in nature, right? You say, okay, start here, and then visit the next set, and then visit the next set, and then visit the next set, right? And so on and so forth. So the other one is sort of the opposite, and it's going to go as deep as possible before, you know, going backwards in a sense, right? So this is depth first search. So what we're going to do is same thing. We're going to pick a vertex to start with. Okay, and we mark it visited. Just like we've been doing in the other algorithm. So then visit any vertex you'd like that's adjacent. Any adjacent vertex. Call it, I'm just going to call it Y, right? So this is another vertex. Mark this as visited. Visited. And now we're going to sort of continue like this. We're going to say, okay, now visit something adjacent to that and mark it as visited. Then choose a vertex adjacent to Y. And continue. So then what do we do? Well, how do we stop, right? Well, we stop as soon as we get to one that has no children, right? So once you reach a node, a vertex without children, we sort of backtrack up the tree, right? We backtrack until we return to a vertex that has unvisited connections. And then we continue along that path. So one of these algorithms is sort of iterative. The other one is recursive, right? In fact, building these in programming, ultimately, you can build them with almost identical algorithms. The difference is one of them uses a stack and the other one uses a queue. Have you talked about stacks and queues?
No. You.
No? Okay. It's not that important. It's just that the point is one of them uses one of them and the other one uses the other. And since computer programs use a stack to sort of decide function calls and stuff like that, that's the one that ends up being recursive because a stack is sort of like that. Both of them can actually technically be done iteratively, but one of them lends itself really well to being done recursive, but it doesn't end up mattering too much. So you know what? I'm going to go back to my philosophy and say, hey, if you have to write it down, so do I. So I was just about to reuse the same tree, and that's not fair. So it is the same tree, so if you want to save yourself some effort, you can. So we've got this sort of structure again. A, B, C, D, this is R, E, F, G, where's the note there? H. So let's perform what this is doing on this tree. So again, we start at any vertex we'd like. Since we have a tree, we might as well start at A. And so we either check A and say, hey, is this what we're looking for? Or we just write it down, right? Whichever we're trying to do. Either we're trying to get everything out of this in a specific order, or we're looking through it to find something, right? So what this says is visit any adjacent vertex. So let's go left to right where possible. We're going to mark it as visited, which we just did. So we write it down. Now it says choose a vertex adjacent to that one that we have not visited yet. D seems like a good pick. And then we repeat. Pick one adjacent to D. Mark it as visited. That's H. Now we reach somewhere that has no children, right? So we can't keep going. So what we have to do is we have to sort of backtrack. Now we get to D and we say, oh, there's nowhere I can go from here that I haven't already been. So we go back again. And we say, is there anywhere I can go that I haven't been yet? Ah, yes, I can go to R. So we visit R, and then we backtrack again because there's nowhere else to go. And then we go to E. Nowhere to go, so we go up, and then we go to F. Nowhere to go, so we go to B. Well, now we've visited everywhere that's connected to B. So we go up again to A, and now we say up. Now we're going to go down the other path. Like that. So you can see here, this produces a different ordering, right? Because in the other one, we had A, B, C, D, R, E, F, G, H. So in this one, we visit H pretty early. In this one, it's literally the last node we visit. So you can kind of see why you would prefer one over the other, right? Like, let's say we knew that there was something we wanted very deep along this path, right? Or a path. We know it's deep. This tree is really, really big and it goes really, really far down and we want to get to something at the bottom. We would prefer this algorithm. Although it does have a problem too of this was the last thing we visited. And in some sense, that's deep in the tree too, right? If we had 2 more nodes like this would still be the last thing we visited. So it's all about balance, right? There's no one size fits all. You just kind of have to pick one and sort of roll with it and accept that sometimes when you're given a choice between 2 algorithms, you might run into the worst case scenario for the one you picked. That's life. You might try to avoid that situation where possible. Like maybe you could sort of do some pre-cleaning on your data and say like, okay, well, I know these are really bad cases for what I'm working with, so let's just pre-screen for them, right? Am I in that situation? If yes, then let's just not do it, right? Like, you know, in this algorithm, if we had something that looked like this, and we were potentially interested in this one, we'd be like, well, does it look like that? Because it's sort of like the worst case for this algorithm, right? Is we want this, we want to visit this one, but this algorithm tells us to go down this deep path first, right? So we could say, do we have any paths that are really, really, really deep compared to all the rest? In which case, this algorithm is going to be kind of bad. And there are things you can do to sort of clean this up, but that's sort of just, you know, algorithms. But one thing I want to mention about this is, I did sort of mention it in passing, this doesn't depend on it being a tree. These actually work for graphs too. And that can sometimes be useful. So this also works for graphs. I mean, trees are graphs, but I just mean it doesn't have to be a tree to work. So let's perform it here. I have this one. Trying to make sure I draw the same picture. That looks like it's right. Hold on. Well, let's just write down the letters and we'll see. A, B, C, D, E, F, G, H. Okay, it is the same. So this is a graph, right? This is not a tree at all. But we can still perform this algorithm on it. Both of them. So in my notes, I started with A. But should I start somewhere else? Does it matter? Do we want to start at A? Yeah, but
Start at center.
Center, so E?
Yes.
Okay, perfect. Let's start at E. So we're going to start here, and I'm going to use this color to indicate we're doing the breadth first, and then we'll do depth first. So the first thing we do is we mark E as visited. We've just been there. All right, cool. Now what we do is we say, all right, let's grab all of the things adjacent to E and visit those. So that's B, D, and F. Okay, and now we just arbitrarily pick to visit the neighbors of the ones we just visited. It doesn't really matter, so we could just do, let's again, so from the board left to right. So we're going to start at B, and we're going to visit everything that is a neighbor of B. So that's H and A. And then we had D next, and we say, all right, now let's visit everything that's a neighbor of D. That's A and E, but we've already visited those, so we don't go back to them, right? So we're just like, we're already done with D. Now we go to F, and we say, all right, visit the adjacent ones to that, G and C. And so again, we see that we sort of have this like, sort of what I would say tiered structure here. And this is all in one actually. So it sort of took 3 iterations through it, right? We started at E, and then we branched out to B, D, and F, and then we branched out from there, right? So this is like a spider web spreading out, right? We just go as far as possible and as wide as possible. Okay, but what about the other one? So we're going to start at E again, and we'll mark it as visited. And we're just going to say, again, going sort of left to right where possible. What we're going to do is we're going to visit neighbors until we can't go any further, right? So we're going to go to B, and then I guess it doesn't really matter which direction we want to go, but we're prioritizing going to the left to right. So we'll go to H next, and then we'll go to G, and then we'll go to F, and then we'll go to C, and then we'll go to A, and then we'll go to D. So in some sense, this sort of led us on a path, right? We didn't end up doing any backtracking here. So in a graph, so in my notes, I do show what happens when you start at A. If you start at A, you kind of go like this, and you get to here, and then you have to backtrack, right? So depending on your starting spot, you might have to backtrack in this. So in some sense, the amount of backtracking you might have to do when it comes to depth first can be quite bad. I would say this is the one I have in my notes where you start at A is another perfect example of like, hey, maybe this would be kind of bad if we didn't pre-screen it. Yep.
Yes, but how does a computer know where to backtrack to?
With a stack. So that's recursively. So this is something you would generally implement recursively. So you would say, okay, start at a specific node, right? And then visit a connected node from there. Arbitrarily, I mean, we won't do it arbitrarily, yeah?
And so the stack contains the locations of the nodes.
Yes, so then if you know what a stack is, once you reach a point where you have no more connected neighbors, you pop from the stack until you have one that has a neighbor, and then you add to the stack again. So that's the idea of how you do this recursively. And if it's built with a stack, you could just do it with a recursive function call, right? You could just say, okay, keep going. What's my terminating case? I have no neighbors. Once I have no neighbors, I go back up, and then I just keep going through my neighbors, right? So that's how this one works recursively. The other one, breadth first. This is just talking about the algorithms and how they work. It is by its nature an iterative algorithm. So again, the distinguishing feature here is stacks versus queues. The breadth first uses a queue rather than a stack. And that means you can't implement it recursively at all. Like it's you probably could force it to be recursive, but at that point you have a very bad and silly algorithm. And it's like, why didn't you just use depth first instead? Whereas both of these can be done iteratively if you really want to. So anyway, the point here is that the strength of the algorithm kind of depends on the node you start with, right? This one, we started at E. It was actually pretty nice. We just went on a straight path through it, and we didn't have to do any backtracking, right? Which in some sense is nice for, I mean, we just found a path that goes through this and visits every node, right? This would actually be, hey, speaking of, we have that's a nice cycle through it. This is a Hamiltonian path, turns out. Anyway, this depends on the node in a graph. In a tree, you would usually start at the root. I can't think of any reason why you wouldn't, because the way a tree is built is from the root. So that's the most easily accessible node, so you would always start there. But in an arbitrary graph, you could start wherever, right? And if you're thinking about the traveling salesman problem where you want to visit all of these cities in sort of the shortest path possible, then you would be starting at one of these cities, right? So it makes sense to have this algorithm work on graphs too. Okay, so something else I want to talk about really quick, just as sort of an application of trees, is a specific type of tree called binary search trees. So binary search trees are kind of interesting. So this is a binary tree. So what that means is there are at most 2 children for every vertex. Right, so something that looks like this, not a binary tree, right, because it has 3 children. So it would be at most 2, right? It could have 0, it could have 1, but it's at most 2 would be a binary tree, which kind of makes sense. As soon as you see the word binary, it means 2. So a binary search tree usually has its vertices labeled with numbers. Labeled with numbers. And satisfies a math property. Because so far so it's interesting because a lot of people look at graph theory and you'd be like, this doesn't feel like math. It feels like math is about numbers, right? No, generally not. Most math is about theory and abstract concepts and that sort of thing. Graph theory is extremely math. But we're actually going to have like a mathematical property here. So if you are looking at a vertex, so let's say you're sitting here, and you've got something like this, and there's probably more down there, right? But you're sitting right here at this one. So there's a specific property of the stuff in the left side and the stuff in the right side. So every vertex in the left subtree, so that means everything down this left path is smaller, and everything down the right is bigger, right? These are numbers, so we actually have a concept of bigger and small, right? So this stuff here is less than this number. This stuff here is bigger than that number. So if you had 10, then this would be, say, 5, and this would be 17, right? All this stuff is bigger. All this stuff is smaller. Now, this leads to kind of a weird-looking structure on these. So when we're talking about, in computing, these types of trees are very, very nice because you can kind of imagine if you were looking for a specific number, well, there's this really nice property of, like, let's say I asked myself, where is 15 in this tree? Well, it's here, and then it's over here, right? So you have a very fast way of looking through this to find your number. It turns out in these, building them is the hard part. Searching them is super easy and fast. It's really nice and convenient. Building up this structure to be like that is quite challenging. So I'll just give an example of an even bigger tree, and I have to be careful here because it does need to satisfy this property, and I have to make sure I write everything down correctly. So this is here, and then we have a node here, and like this. So we start at 8, 3, this is 1, 6, 4, 7, this is 10, 9, 14, 13, and 16. So it's kind of funny here because these trees have a sort of a misconception about them, right? So when we say that everything on the left is smaller, that's true for every single one of these nodes, right? So it's not necessarily in ascending order, right? It's, you come to here, all we know is the left stuff is smaller, the right stuff is bigger than 3, right? So 6 comes here, and then this is smaller than 6 and bigger than 6. Right? And so on and so forth down like that. So if we want to search this, to search for a specific number, we start at the root. Is that our number? I mean, if it is, then we're done. Cool. If not, is our number bigger or smaller? If it's smaller, go left. If it's bigger, go right. Go left, go right. And then just repeat until either you find it or you run out of places to go, right? Because let's just do some examples here. So let's say we wanted to find 4, right? We're looking for 4 in our tree. So we start here. Is 8 equal to 4? No. But 4 is less than 8, so we're going to go down this path. So now it doesn't even matter what's over there, right? We already know that it's bigger than 8, so it's not relevant to us. And then we say, okay, now I'm here. Is 3 equal to 4? No. But 4 is bigger than 3. So now I go down here. 4 is not 6, but 4 is less than 6, so I go down here. Ah, there we go, right? So 4 is in this tree. What about 12? Same exact thing, right? We say, okay, I've got my 12 here. Is 12 equal to 8? No. So 12 is bigger than 8, though. So I'm going to go down this path. Is 12 equal to 10? No. It's bigger. Is 12 equal to 14? No. 12 is smaller. Is 12 equal to 13? No. So is it bigger and smaller? Well, it doesn't matter. There's nowhere else to go, right? So now the interesting part about this is once we get to here, we don't backtrack or anything like that. We just say, it can't be in the tree. Right? So we can see in terms of going through this tree, we checked like 3 things, 4 things, right? It was very efficient to check for this. So for these are called BSTs, are fast and easy to search, but hard to build. And I mean, you could just kind of imagine it. Let's just say you had some list of data, right? Like it's an array of numbers. And you wanted to turn your array of numbers to match this structure. It's going to be quite challenging, right? Because your array might be in a random order, right? So how do you do that? Well, there's a couple of things you do. You just basically pick somewhere in the array, either the first element or the middle element, whatever, and you just say, that's the tree, right? And then you start picking elements and putting them where they're supposed to go. But that can lead to like a really nightmarish tree. Like if you pick the largest number in your array and put it here, then there's going to be nothing down this side, as an example. So there's this idea of balancing these trees. It gets really, it's a lot. Mathematically and computationally, it ends up being a lot. But I think they're very interesting because you can see they're very efficient. When you have them, they're really nice, right? Because you could just look through them very fast. And they have this sort of interesting structure of, I think it's in order traversal, which I didn't talk about, but don't worry about it, would produce the numbers in ascending order. There's like a specific way you can traverse this tree once it's built to get every number in ascending order, which I think is interesting. So I think it would be, yeah, it's in order. Here, 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 here. Yeah. So anyway, that's basically all I've got for trees and graph theory. These are all just things that I thought were interesting, right? They're all of them have uses. All of them are things you could very easily run into in your journey programming. So unlike the previous topic I had, which was proofs, you would literally never run into any of those in your entire life. So it's like, what's the point? Why am I talking about this? Whereas binary search trees, pretty unlikely that you would run into it. I just think they're an interesting thing to talk about. But the traversal algorithms, the search algorithms, it's conceivable that you run into that, right? You'll just be looking how to tackle some problem, and then on Stack Exchange, they'll just be like, oh yeah, I just built a binary tree, and then I did depth first search, and it solved my problem. And then you'd be like, wow, I'm sure glad I forgot about the thing that Travis talked about, but I remember he talked about it. And then you'll learn it there again, that's just learning. But they pop up everywhere, right? And these traversal algorithms also pop up everywhere. So that's why I decided to talk about it. Everything I talked about graph theory was in service of getting to the trees. Okay, any questions before we hop into the quiz? The quiz, so normally I can say this based on past experience. I'll be like, so the lecture we just did seemed really hard, but I promise the quiz when you do it is not too bad. Like recursion, right? The lecture seemed like a lot, and then everyone actually finished the quiz within like half an hour. Like most people were done it real fast. I don't know for this one. I have it's color this graph, and then it's do those like a breadth first and depth first traversal of a tree. So I think it's gonna be not too bad, but it's one of those things where you miss every shot you don't take, right? Sometimes you take a shot and it sucks. If everyone's like struggling to do it, then I'll be like, okay, I'm gonna be very generous and I'll change it to be better next time. But it's also possible everyone will be like, oh, that was a pretty easy quiz, thank you. So I guess we'll see.